I will talk about the process of structure solution and refinement using EXPO. You can find this presentation into the shared folder called presentations. Okay. And EXPO is a program able to perform all the steps of the process of crystal structure determination. The entire process of a crystal structure determination can be essentially divided into 3 stages. The first stage, probably you know, is the indexing and the space group determination. During the indexing, cell parameters are determined, and at the same time, you have the assignment or HKL Miller indices to each reflections. In the second step, EXPO require the knowledge of unit cell content. In other terms, you need how many atoms of each kind are into the unit cell. When the unit cell content has been established, the next step is the calculation of initial structural model using direct methods or direct space methods. This initial structural model is only an approximation of the real structural model, and the last step is the refinement of this initial structural model, typically using the refill method. EXPO is a software essentially devoted to the structure solution, and this is the reason why I dedicate a large part of my presentation to the structure solution, and that sometimes structure solution might be the challenging step in the process of crystal structure determination. To get started with EXPO, first of all, you have downloaded the software from this link. And for Windows, the installation is very simple. You have to download the installer and follow the standard setup installation. For Mac, I have prepared on Monterey the DMG package that, but it should work also on a later version of Mac OS, but only on Mac with the ARM architecture and not on all the Intel architecture. Okay. For Linux, the best approach is to install using, in particular on Debian distribution, using the prepared package. And in this package, you can find the parallel version of EXPO. And or you can install compiling the source code of the program. Keep in mind, if you want to run the indexing using DickMol and MacMy, on Linux and on Mac, you have to install the software Wine. There is a link into the installation instruction that you have to follow to install Wine. One is just a famous emulator of Windows application for Linux and Mac. Okay, in this slide you can find some useful link. This link contains the instruction for the installation. The second link you can find the documentation and the reference to the main features of the program EXPO. And the last link you can find some practical examples. Okay, some technical details related to EXPO. EXPO is a program written in Fortran and C++. The program was built using OpenGL for the 3-dimensional molecular visualization, and the graphics interface was originally realized using GTK, but we migrated first to Qt5 and then Qt6 for the graphic interface. Is released under the LGPL version 3 license. And okay, speaking about structure solution, the techniques that are currently available for structure solution can be divided essentially into 2 different approaches. The traditional approaches, in the traditional approaches, the aim is to extract the integrated intensity for each reflection and use this intensity in the same type of calculation that has been developed for single crystal diffraction. And the most important traditional approaches are direct methods and Patterson methods. In direct space methods, the trial crystal structure are generated into the unit cell, and the suitability of which trial crystal structures is evaluated comparing the experimental diffraction intensity with the calculated diffraction intensity from the trial model using appropriate figure of merit. These methods have become widely available and popular. Probably they are the most important method used for the structure solution and been applied to organic, inorganic, and organometallic compounds, but in particular they have found great utility in the structure solution of organic molecules, because in the case of organic molecule, normally the chemical connectivity is known, and for organic molecules, so it's more easy to translate this information in a three-dimensional model. That is an important requirement for the structure solution by real space methods. I will cover direct methods and direct space methods in this presentation. There are other methods. Probably the most popular is the charge flipping. And what I'll say can be applied to X-ray and neutron and also electron diffraction. So, as you probably know, an important stage of the process of a crystal structure determination is the extraction of the integrated intensity for the majority of reflection. This procedure is called wall powder pattern decomposition, and can be performed using essentially two methods: the poly method, that is least square refinement, where variables are the intensity, and the LEPAD method, that is an iterative method for the extraction of the integrated intensity. The default approach used in EXPO is the LEPAD method. Okay, the first example that I will show is the structural determination of this simple organic molecule. And all the required information are the experimental diffraction data and the molecular formula of this compound. This is the result. So you can find the required file in the folder examples, and this file, okay, you run terminal. And so you can find here the input file of the program EXPO. This is the input file has the extension EXP. This is a typical input file for EXPO. You can edit using your favorite text editor, for example, JEdit. Okay, and the input file is a sequence of commands and directive. The commands start with the percentage symbol. And after the command, you can find some directives that are used to add additional information to the command or to change some default strategy of the command. Percent job is just used to specify a text line just for annotation. In this case, I specified the chemical formula of this compound, this organic. Percent structure is used to specify the file name of the output file generated by the program. And the most important part of this input file is percent data. That is the command used to add information about the experimental diffraction data. In particular, the file name. After pattern is directed, you have to specify the file name containing the experimental diffraction data. And remember, if the input file and the data are in the same directory, it's not necessary to specify the full path. You have to write only the name of the file and the wavelength used. And after we add these two commands, percent and trail and percent equal, we have to specify that we want to perform the indexing using an trail program and equal program. And at the end, we have the command percent continue to say we want to continue the process of crystal structure determination with the next step. The next step is the determination of space group and structure solution. Okay, you can run the input file from file, load and go, or you can run from command line, just EXPO now in this way. So, okay. Remember the first step is the indexing of the powder diffraction pattern. You have to click next, and a preliminary quick search is performed. At this level, it's important to inspect your diffraction pattern to check if all the most important peaks, in particular at low angle data, have been selected. And if necessary, you can add or delete peak. You can change the peak search condition from file peak search condition, and you can, if necessary, you can modify the background. So the next step is a refinement of peak positions, and then indexing using two programs, entry or default. So at the end, you will obtain a list of plausible cell parameters. And in this list, you can read in this column the type of program used for the indexing, and for entry or default default, the cell parameters, the cell volume, some figures of merit, the shift applied to the diffraction pattern, and in this column you can read the number of an index lines that in this case is 0, but sometimes you can obtain any integer number, for example 1. Index line means that you have some peaks selected in your diffraction pattern, and you don't have the associated reflection. So the indexing procedure was not able to to find a cell that can be match the selected peak. This is the typical situation when you have impurity lines in your diffraction pattern. Or if you have an index line, another possibility is that your cell parameters are wrong. So the indexing procedure was not able to identify the correct cell. And then I select the first cell parameters and then OK. The next step, remember, is the determination of the space group. At this level, the unit cell content is required. First of all, I type the molecular formula that is 15. Again, this is the molecular formula, and this is the cell volume, and this is this number that you currently is the volume of the molecular formula. So it's the molecular volume that is calculated using the average atomic volume of each atom. And so if I divide the cell volume with the molecular volume, I can obtain the number of molecules inside the unit cell. So this number should be 4, not 2, because these two quantities should be approximately the same, but 4. At this point, you can see that the cell volume and the volume of the content, so the volume of 4 molecules, is approximately the same. Here you can read the volume parameter that is calculated assigning 18 angstrom cubed for each non-hydrogen atoms. A resolution value should be 18 or in the range between 16 and 20. So I click play, and the next okay, at the end you will obtain, after the procedure of the space group determination, you will obtain a list of, in the first column you can read the space group, in the second column you can read the extinction symbol, then the figure of merit associated to the extinction symbol, and not to this figure of merit is not associated to the space group but to the extinction symbol. This means that space group with the same extinction symbol have the same figure of merit. And in this column, you can read the number of systematically abstract reflection used for the determination of the space group. This is the L8 seal is the number of expected atoms into the asymmetric unit. And in this column, you can read the frequency of the space group, reported in terms of the number of occurrences into the crystal structural database, the percentage of the space group, and the rank of the space group. And in the last column, you can read if this space group is chiral or not chiral. This information can be useful when you, in particular, when you are trying to solve an antimaterically pure crystal compound, because in this case, you expect that the space group should be a chiral space group. And so the program asks you if you want to transform, because P to 1 over A is not the standard settings, but okay. And at this point, the program writes an input file containing the cell parameter and the space group. And you can use this input file in the future if you want to perform only the structural solution without repeating the indexing and the space group determination. The next step is the structural solution with direct method. Okay, and all these seconds are required. Okay, and this, okay, and this is the result. You can recognize the molecule and without the hydrogen. So, but if you want to, you can, there is a tool to add automatically the hydrogen atoms. Okay. And we have a model that can be used for rate refinement. And in EXPO, the rate refinement is accessible from refine or rate field. Okay. And I will just continue with my presentation. Okay. This is another example that you can find in the tutorial at this link, and this example that is a structural solution of this is the structural determination of symmetry in its accessible from file load example. And this is another example that you can find in folder examples. In this case, we are assuming that the cell parameter and the space group have been already determined and is the structural solution of this inorganic compound. And okay, sometimes direct method can fail to determine the correct structure. An alternative approach in this case is to try to explore all the sets of phases generated during the direct method procedure. I will explain in detail, but first of all, I will run the example. The example is in the folder peptide wire. Okay, so your that one. Just we will see that in this case, direct methods fail to locate the correct structure. And okay. Or it's possible that some atoms that will obtain to be correct, but you can't recognize the correct structure in this case. So a possible approach that you can use is to click Solve, Explore, Trial, and Explore Trials not processing. All the first tile has been processed, and you click on Explore. I will explain while the program is running. This is a procedure that requires some minutes. Yeah, I have this slide to explain in more detail. This is a diagram of the direct methods steps. So the most important step in the direct methods procedure is the tangent procedure, where is an iterative procedure using the tangent format to generate the phases. Okay. And in EXPO, 20 sets of phases are generated, and these sets are ranked according to figure or merit, and only the most reliable set of phases is used to calculate an electrodensity map. Because if you have the phases, if you have the structure factor amplitude, you can calculate an electrodensity map by inverse Fourier transformation, or in other terms using this mathematical formula. And this initial electrodensity map is optimized, and you can obtain a structural model. If this structural model is, you see that is chemically reasonable, you can continue with the next step, that is the refinement, or you can select a new trial. In EXPO, there is a procedure to automatically test or evaluate all the trials of phases generated by the program. And so you remember you have to select in the menu Explore Trials and click on this check button and then Explore. And at the end, because we have 20 sets of phases, at the end you will obtain 2 anti-structure models. And okay, probably is not, I think, okay. It's okay, it's slow procedure. We will check later. And so we have seen that, just as a reminder, this is the input file that you have to use if you want to perform the structure solution starting from the indexing. But if the cell parameters and the space group have been already determined, this is the space group. You have to write the cell parameters and the space group using the directive cell and space. Okay. There are some structures, some components that can be solved using direct method. In particular, the structure, the limit of the direct method is into the number of atoms into the asymmetric unit. So this means that if you have big structure, for example, this is a small molecules, but you have 4 of these molecules into the asymmetric unit. So this structure is difficult to solve using direct method. And the same, in this case, you have 2 molecules. And so you have big structures in terms of number of non-adjoint atoms into the asymmetric unit. And sometimes you put there other problem. For example, you have broad peaks and severe overlap, or you have a small 2-theta range. This is very common, in particular, if you are collecting using this for a laboratory the organic market, because you have that at the high angle, you have weak intensity, or sometimes the intensity are not detected at all. So you have this combination of large molecules and not good quality data. And so in this situation, direct methods can fail. Fortunately, we have other methods that we can use. And the most important alternatives are presented by a real space method called also global optimization method. When you solve an optimization methods, if you have solving an optimization method means that if you have a real function of several real variables, you are searching for the minimal function value corresponds to the minimal function value. Okay. So we can see the problem of structure solution as an optimization problem, where the variables are the fractional coordinates of your model. But there is a best approach, in particular to reduce the number of variables. It's the best approach is to describe our system in terms of molecular fragments. And for each molecular fragment, we have 3 variables related to the fractional coordinate of the center of mass. The orientation of this molecular fragment can be defined by using the orientation into the space can be defined using 3 angles, and the intermolecular geometry can be described using a set of torsion angles. This description can be extended to other molecular fragments into a unit cell. The problem is that we are exploring the n-dimensional hyperciphers, and this subset contains many local minima corresponding to a false, not correct structural models, and we have only a global minimum that corresponds to the correct structure. And so to solve this problem, we can't use the local optimization method, because local optimization methods are able only to locate the local minimum close. For example, the non-linear least square used for refinement are able only to locate the local minimum close to the starting model. But in this case, we have to use global optimization method, because these methods are able to, first of all, to escape from local minimum, and in theory, they are able to reach the global minimum from any random starting model that you choose in this hypersurface. This method can be traditionally divided into deterministic and heuristic. What is the most important thing is that the algorithm using crystallography are heuristic algorithm, where heuristic means that they are trial and error algorithms. Sometimes they are called meta-heuristic in the sense they use special tactics and strategy to look at the global minimum, and this approach are inspired to natural phenomena, as their name suggests, because, for example, you have ant colony optimization, particle swarm. The most common global optimization method used in crystallography is simulated annealing. It's because, first of all, the simulated annealing is very effective in the process of crystal structure solution, as few control parameter is not difficult to understand. So in particular, they can be easily converted into computer code, and several codes are available to test for structure solution. Important modification of this algorithm are the parallel tempering, and in particular the adaptive simulated annealing. In general, the algorithm of simulated annealing using crystallography are adaptive. Adaptive means that some parameters are not constant but dynamically modified during the progress of the search. And this is a list of programs using the global optimization methods. And I will quickly describe the simulated annealing steps. So the simulated annealing involves the generation of a sequence of trial space structure. Each trial structure is generated by the previous by random displacement of structure variables. And for each trial structure, the cost function is evaluated, and the trial structure is accepted if using depending on the metropolis criteria. So if the cost function goes down, the trial structure the newest is immediately accepted. But if the cost function goes up, the new trial structure is accepted using this if this condition is verified, where R&D is a random number. And there is a parameter that is really important, is the temperature factor. The consequence of the application of this formula is the higher is the temperature of the system, the more likely is that an uphill move will be accepted. And these steps are repeated. And to simplify the algorithm, I will call this sequence of steps annealing step. So the annealing steps are repeated several times, for example, L times, and then the temperature factor is reducing, multiplying this, for example, for a beta factor, and these steps are repeated until a stopping criteria is satisfied. So this is the graphic interface that you can find in the software EXPO, and the most important parameters are the number of the the number of moves that are the number of moves is that you can find here, and is a number proportional to the annealing step. And so if default value is assigned to the number of moves, but if you see at the end of a structure solution that the program can fail and you don't see a reasonable structure solution, you have to modify these parameters. And another important parameter that you have to modify when you see that the structure solution failed is the number of simulated annealing RAM. This means that the global optimization method in general are stochastic method. This means that that it is guaranteed to locate the global minimum only in infinitely long run, but it's not possible to perform an infinitely long run. So in general, a relatively long run are performed, and the default number of runs in EXPO is 10. But if you see that the algorithm fail to locate the global minimum, you have to increase this number of runs. In particular, if you are solving complicated problem with large number of internal degree of freedom, for example, you have more than 50 degrees of freedom, you have to increase the number of moves and the number of runs. In EXPO, the number of moves is automatically calculated considering the number of molecular fragments, the number of external degrees of freedom, the number of internal degrees of freedom, and taking into account the flexibility of your molecule. Because if you have, for example, a sequence of the torsion angle connected to form a long chain, this could be a complicated problem for the structured solution using the real space methods. Okay, in this slide you can see also a comparison between the traditional approaches and our space methods. Traditional approaches, first of all, are not able to use actively in the process of structured solution the chemical knowledge. In direct space method, the chemical knowledge is the aspect that does determine the success of this method, because direct space methods are able to incorporate a massive amount of chemical information into directly in the process of a structured solution. Another important aspect, the complexity of problem in the case of a traditional direct method or fat transfer method depends on the number of non-hydrogen atoms in the asymmetric unit. In the case of direct space method, the complexity depends on the number of degrees of freedom. This means that you can solve big structure using direct space method, but if this big structure contain only few degrees of freedom, this is an example. This structure could be difficult to solve by using the direct method, but can be easy to solve using real space method, because we have only 8 degrees of freedom. So it's a simple project. The consequence of the application of direct space method is that today you can solve structures that are too big to be refined using Refinement method, because you have a large number of variables, and sometimes you could have only X-ray diffraction data, and so the Refinement method is structured X-ray laboratory data. So in this case, you have big structure, a lot of variables, not good quality data, but the quality data is sufficient to solve the structure, but not to refine the structure using Refinement method. Another difference, the traditional approaches take advantage by using data of higher resolution, for example, using synchrotronization data. In the case of direct space method, you can solve structure using X-ray laboratory data and with a small to theta range, because it's, for example, EXPO, the default resolution used for the data is 2.5, but in general you can solve in the range of 2.5. And traditional approach generally require less time to run, but in the case direct space method require more time and patience, and in particular for large molecules you have to use faster computer, you have to run your computer overnight, and if you are very complicated problem, you have to use parallel parallel machines to run the program. Another difference between, in my opinion, between traditional approach and direct space method is direct space method should be associated to, at the end of a process of structure solution, to a validation step using, for example, computational chemistry. In the case of traditional approaches, these steps of the final step of validation of structure cannot be necessary, because when you have seen when you solve using direct method, you see the structure that appears from nothing using just Ricci Fourier transformation. And so in this case, you don't have a starting model. So in general, in the case of direct method, a validation step at the end is not required. Okay. Another important step is the process of building starting model from real space method. When you apply real space method, it's important to know the molecular connectivity of your compounds. This is not a big restriction if you are solving, for example, molecular compounds, because molecular compounds, for example, organic molecules, in general are alive for controlled synthesis, and there are some analytical techniques that you can use to obtain quickly and accurately information about the molecular connectivity. So in general, the molecular formula, when you see a real space method, is not sufficient. And because the molecular formula contains only the information about the number and the type of atoms, and you need the structure formula, because the structure formula contains information about the connectivity and about the type of bonds. For example, if you have simple double bonds. So this is an important information to build your starting model. Any crystal structure can be described as a combination of building blocks or scattering of objects that could be isolated atoms, molecule, or more in general molecular fragment. And in particular, in the case of non-molecular compounds, you can use for coordination polyhedra. And essentially, there are two different methods that you can use to build your starting model. If you are solving an unknown compound, it is likely that a big part of your structure is a part of another structure that has been already solved and deposited into a crystal structure database. So the first action that you have to perform is check for similar molecules into the database. Okay. And as you probably know, the most common database in particular for organic and for organomethylated compounds is the Cambridge Structural Database. There is an equivalent commercial database for inorganic structure, the ICSD. And the code is a general database containing organic, inorganic, and organometallic database, and it is free database. And probably you know that when you retrieve a molecule from this database, you could have a zip file. Zip file is the most common file that you can use to exchange information in crystallography. At the same time, there are some free chemistry databases that you can use to have, in general, chemical information about your compounds. But in particular, you can download, for example, from Package, you can download a three-dimensional representation of the molecule. And you do that, you download an SDF, an MOL, or an MOL2, or you can find the SMILE string of your compound. So you can download files that then will be imported in the software that you will use for the real space methods. And in EXPO, there is a graphic tool that you can use to build query for the crystallography open database and directly import the crystal structure into the software. And the second approach that sometimes can be combined with the using of database is optimize the molecular geometry using computational chemistry. First of all, there are three different levels of that, or theory that you can use for the geometry optimization. You can use molecular force field that is very fast and sometimes accurate, in particular for organic molecules. Okay, sorry. And then you have semi-empirical methods that are faster than, for example, other methods, for example, set-consistent methods or DFT methods. And then are ab initio methods that are artifact methods or density functional theory methods. And there are several free programs that you can use to perform this type of calculation. A possible strategy is use the output of the output geometry of molecular force fields as input for the semi-empirical methods and output geometry of semi-empirical as input for the FT calculation. Yeah. Okay. In EXPO, you can find the most important program that you can use for semi-empirical calculation is MOPAC, and in EXPO you can find a graphic interface to run MOPAC. You can automatically create the input file for MOPAC, run MOPAC, and visualize the results of this program. This is a third-party software. You have to download the software from this link and install this software in a standard folder. And in EXPO, you can run the geometry optimization by using a molecular force field. And at the same time, you can create input file for a limited number of quantum chemistry package, for example, new chem, Gaussian, crystal, Abinity, and quantum express. And sometimes you need a molecular editor. A molecular editor is just a software, an external software that you can use to sketch molecules in 2D or 3D to optimize the geometry by using force fields, to create the input file for quantum chemistry calculation, and to read the output file created by other computational packages. And this is not an exhaustive list, it's just a list of the software that I have tested. Okay. And so in general, the process of building a starting model is a two-step process. The first step could be the structural optimization. And then you have to export this three-dimensional representation in a file, for example, MOL, format files that can be imported by the software EXPO. In this case, you can see that the starting model contains 2 fragments, and we have 6 degrees of freedom related to the orientation or translation of this fragment. You have 3 external degrees of freedom related to these isolated atoms, and then you have two torsion angles, that rotatable torsion angles, because in the generally during a real space method, the ring conformation and bond angles are not modified. So are the internal degrees of freedom modified are only the torsion angle that can be rotated. You can't rotate, for example, the torsion angle inside a closed ring. In general, the configuration of a ring is not modified. So it's important that in the starting model, the configuration of angles and the ring conformation should match as close as possible that of the correct structures. So, okay. And another example is this. If you are solving molecular group balancing generally, it's the classic situation here is that you have one molecule in the asymmetric unit, and but sometimes not very frequently you could have, for example, 2 molecules into the asymmetric unit. For example, if you are solving the crystal structure of S-ibuprofen, the space group is 2-1 or 2 P21 over. And in this case, you have 2 molecules into the asymmetric unit, so you have to build the 3-dimensional representation of the molecule of ibuprofen, but you have to duplicate. Okay, this is trivial because essentially your starting model should be not a representation of the molecule, but should be a representation of the asymmetric unit. So if you have 2 molecules into the asymmetric units, you have to input into the software 2 molecules of the starting model. Okay. And I will show as example the structural solution using the array space method of the molecule of ibuprofen. And okay, the only required information in this case are the experimental diffraction pattern and the structure formula. And first of all, we have to build our starting model, and we will use the program ChemSketch. Okay. Case this. This is the final result of the when you explore our set of phases using the direct methods. And you can in this list you have 20 structural models, and the first model is the correct one. Okay, so we have to go into the folder ibuprofen. I can put this on terminal. Just first of all, we have to build the ChemSketch. Okay, this is a free software that you can use to build starting model. First of all, you have to just draw your structure. Okay, so just it's so we have a carboxylic group in this part. Okay, so we have to change cannot this. Okay, just some seconds. Okay, this is the plain structure of the ibuprofen. You have to draw your structure. That is very simple. You can use this program or other program. And at this point, the most important part we have only is that you have to convert this plain representation of the molecule into three-dimensional representation. And in general, you have to find an option like this, 3D structure optimizer. Okay. And at this point, you can save. You can go from export, and you can save in them as a MOL format. Okay. I don't save because I already have this small file set and clear. And this is the input file for the structure solution by real space method in EXPO. In this case, I am using an SDF file that of the ibuprofen that I downloaded from PubChem. Okay, the input file, in this case, we are assuming that cell parameters and space group are already known, and you have to use this command called %fragment. Okay, I will explain the input later, and I will run just you can run using EXPO ibuprofen, and you have to click run. Okay, or an alternative approach, and it is very fast. You can run okay. You can run the parallel version of the program. You have to run because EXPO is the parallel version is like I will explain later in details in the next slide. To run the parallel version on Linux, you have to write. First of all, you have to specify the launcher. The launcher typically for MPI application is MPI run. And then you have to specify the number of tasks. Okay, 10 tasks. Okay, then the number of application, and then the parameters of the application. This is a general method to run an MPI application. You have to specify with the option -np the number of tasks. Number of tasks means that is the can be associated to the number of CPU cores, but it's in general the number of tasks doesn't exceed the number of CPU core to avoid degradation of the performance. Okay, okay, so you run the and okay, I continue. Okay, and just and just terminal here. So we have action. No. Okay. Just a problem to zoom on this slide. Okay. Okay. Just finished. And okay. And when you run, first of all, when you run the MPI application, you don't have the graphic interface. But at the end of the process, the program generates a project file, and essentially this project file is the name of the output file and .expo. So you can write, and at this point you can explore if at the end of a real space method. First of all, you can see the graphic interface in this tab. You can see the general information related, the general condition related to the application of the algorithm. In the top crystal, you can read the external, the internal, and the correction. That is only the correction for the preferred orientation. And so, for example, if you click, you can see the internal degrees of freedom. Okay, and at the end, you can explore the solution. Okay, this is a simple test. So we have always the same solution. Yeah, maybe you can see the difference between the first and the last. And for each, remember we performed 10 rounds of simulated annealing. So at the end of this time around, we'll obtain the structural model that are saved into this C file. In fact, if you go in the folder, yes. Okay, you can see here, you will find 10 files. Yeah, you can see 10 files. Yeah, corresponding to each structural model. Okay, so this is my first example related to real space method, and we can continue the presentation. Okay, just as a reminder, remember that this is the typical input file for the structure solution by real space method, and remember the command %fragment is the important command to load the starting model, and then you have to add this command %STNearly to run the real space method procedure. And %fragment is a powerful command because if you associate this command to a keyword, you can, for example, load into the program some specific geometry that are, for example, dodecahedra, octahedra, or you can use this keyword atoms to load isolated demo atoms, but we have specified the formula. For example, if you write O3, 3 isolated oxygen atoms are imported into the program. Or you can load a model specifying the SMILE string. And you can run, remember that you can run the program without the graphic interface. Okay, if you run the program using MPI, automatically the graphic interface is you don't have the graphic interface, it's suppressed. But if you don't run the graphic interface, but you want to run the program without the graphic interface, for example, if you are running the program on a remote computer, you have to add the option -no GUI. Okay, this is another example that you can find into the tutorial that you can access by using this link. And you can run the direct space solution without writing the input file, you just using the graphic interface. So you have, first of all, you have file, click on file, import diffraction pattern. First of all, because you need the diffraction pattern. And second, you need the starting model, and you can import the starting model from file, import structure. And if your starting model contains many molecular fragments, you can you have this molecular fragment into a separate file. So you have to import the first fragment, and then you have to add the other molecular fragment. From structure, modify, add fragment, and then you can solve the structure clicking on solve simulate NNA. And this is another example. As I said, when you are solving molecular compounds, sometimes you have that in general the asymmetric unit contains one molecule. Sometimes the asymmetric unit can contain two or more molecules. In other situations, it's possible, in particular, if your molecule has a symmetry element, it's possible that the asymmetric unit contain a half molecule or a small fraction of a molecule. This is an example. In this case, okay, you have to pay attention. First of all, you have your molecule. You have to perform a 3D structure optimization. And the best approach in this case is to consider only the asymmetric unit. So you have to consider only the half molecule. It's possible to solve the structure considering all molecules, but if you combine the direct space method with the application of dynamical occupancy correction, that I will talk about this algorithm in the next slide. But the best approach is consider half molecule, because this is a recommended structure. The other structure is really slow. It is not suggested. Okay, another situation could be, for example, if I have, first of all, when you import, you have seen that when you import a starting model into EXPO, the program automatically identify all the torsion angles that are rotatable and are parameters for the real space method. So, and in default, all these torsion internal degrees of freedom are optimized. But sometimes I know that in my molecules, I have some part of the molecules that are with fixed geometry. The typical example is, for example, if I have double bonds, these double bonds could be, this double bond is not in a ring. So it's, for the program, this double bond is a rotatable torsion. But in general, you know that the configuration around double bonds is planar. So if I want to I can introduce this information in the process of optimization. I have to unfix. I have to say to the program, don't optimize this parameter, because I know that the geometry is planar and I know the configuration. In this case, I know that this part of the molecule is planar for conjugation effect, so I can unfix these variables. So I can reduce the number of variables and I can reduce the time required for the optimization. At the same time, there is another aspect I am introducing in the process of starting solution, the structure solution, more chemical information about the structure solution. Other aspect, typically in the process of real space method, the stereochemistry is not modified. This means, for example, if I have a diastereoisomer and I don't know the configuration of the chiral center, in this case, I have to test all the possible diastereoisomer. Okay, so if I have, for example, this model with two chiral centers, I don't know the configuration of chiral center, I have to test these two diastereoisomers. Okay, it's not necessary to test SS diastereoisomer or SR, obviously, because with power diffraction it is not possible distinguish between RR or SF. Okay, so I have to test. So I have 4 n-terminal, but I have to test for structure solution only 2 diastereoisomer. And another approach that you can find in the literature is to remove this chiral center, for example, breaking 2 bonds And in this case, I have 3 molecular fragments, but I can add restraints between this. For example, if I break this bond, and if I break, I have 3 fragments, but I can add restraint to keep the information that these 3 molecular fragments are connected. And I could have the inversion of the kilocent, so I can use only 1 starting model and not 2. Okay, this could be interesting, particularly if I have more chiral centers in my molecules, so I cannot prepare several starting model. Okay, most simple situation I told you about the double bonds in particular. If I don't know the configuration around the double bonds, I have to prepare two different starting model. Or an alternative, I can optimize this double bond, expecting to obtain at the end of the process of structure solution the correct configuration of the double bond. Another critical situation is when you have, and you have to pay particular attention when you have molecules containing non-planar ring system, and I will tell you about this problem in the next slide. Okay, in the other slide, not this slide. Okay, in this slide we have other information related to the H atoms. The H atoms, the hydrogen atoms do not contribute significantly to the X-ray diffraction, so they have a low scattering factor, so they can be ignored during the structural solution. In particular, if you are solving complex problems when you have a large number of the degrees of freedom. My suggestion, if you are solving a small molecule, is not necessary to remove the hydrogen atom. But if you have big problem, complicated problem, it could be better to remove hydrogen atoms, and so you can reduce the computational time because if you reduce, because in general in the process of real space method, the bottleneck of the algorithm is the calculation of structure factors. And into the calculation of structure factor, there is a loop over the number of atoms. So if you reduce the number of atoms, you can reduce linearly the time required for the calculation of structure factor and the time for the use by the entire algorithm. In EXPO, there is a directive that you can use to remove the hydrogen atoms, and the name is delete hydro. And if you have removed the hydrogen atoms, you can add using another graphical tool the hydrogen atoms. These graphical tools add the hydrogen considering only the geometry of the functional group. So it's able to recognize if you have a methyl group or if you have double bonds. And okay. But pay attention when you use this tool, that this tool can be undetermined, the position of the hydrogen atoms in some functional group. For example, if you have methyl group, you are not sure about the orientation of the hydrogens in this group or in this situation. Or the same situation you have if you have for the hydrogen in oxidoryllic group or into the primary mide. Okay, there are other approaches that you can use to refine this type of hydrogen atom, for example, using computational chemistry. And there are several options in the simulated annealing. And okay, the resolution, as I said, the default value for the resolution is 2.0, and this value is used to remove the part of data at high angle. So, and in other terms, if you increase this number, you increase the number of reflection, and remember, you increase the time required for the computation. And okay, there is the okay. I told you about the number of moves, the number of runs. And okay, starting temperature reduction are not really important. Are the factor specific of the simulating, and typically I don't modify these parameters. And remember, the most important parameters are the number of moves and number of simulating and run. And okay, this slide is dedicated to the cost function used in EXPO. In EXPO, we have two cost functions for the real space method. The first cost function is the same cost function that you have into the refinement. You have this sum over all the data points, and you have a difference between the experimental intensity and a calculated intensity. But okay, essentially this is not all profile R factor, because this calculation is performed only into a limited range around the peaks. We have a peaks, and you don't use the entire pattern, but you use only a small range corresponding to the peak position. So this is a strategy to reduce the computation time of the cost function. Okay, there is another cost function. Okay, the first cost function does require the extraction of integrated intensity, but the cell parameter, background, peak shape profile parameters, shift parameters should be refined using linear least square that is performed before the process of a real structure solution. And another cost function is the integrated intensity R factor. And in this case, we have the comparison between the experimental integrated intensity and the integrated intensity calculated by the trial structure. And the application of this cost function requires the preliminary extraction of integrated intensity. And each of these cost functions can be combined with the other cost function that can be used to introduce additional information into the process of crystal structure solution that are geometry restraints, bond volume restraints, and anti-vampire restraints. Okay, another typically the program used for real space methods are applied to molecular compounds, because the reason is that molecular compounds are, you have a molecule that you have into the solid state, that molecule that are isolated building blocks, that are connected by weak intermolecular forces, for example, van der Waals forces or hydrogen bonds. So in this case, it's the molecule is naturally a building block. So, for example, if you are solving the crystal structure of parasite 1, your starting model is the molecule of parasite 1. But if you are solving a non-molecular profile that are constructed by a network of chemical bonds extended into 3 dimensions of the space, it could be not easy immediately identify your starting model. So in general, the approach is to describe, for example, in the case of this compound, as a combination of isolated atoms and coordination polyhedra. For example, I can describe this molecule as a combination of 3 tetrahedra of phosphate molecule, and 2 isolated antimony atoms. Or if I have the information that the geometry around the antimony atoms is octahedral, I can introduce this information. So I have, in the second case, more chemical information, but more degrees of freedom. And here I can always solve a structure starting from isolated atoms without no chemical information, but the algorithm can fail if you have large number of variables into the system. And when you solve non-molecular compounds, you have some problem. The first problem is, first of all, you cannot know the number of coordination polyhedra to input into the unit cell. And the choice about the number must be made considering how many atoms are expected into the unit cell. Another problem, you cannot know the type of polyhedra to introduce, and at this point, it could be important to try to find similar structure into database or into the literature. Another problem is that non-molecular compounds tend to crystallize at tight symmetry, and at tight symmetry, you could have that some atoms can can lie on a special position, and in general, you don't know which atom will lie on a special position. So it's important that the algorithm must be made able to automatically locate which atoms will fall on special position. And this is not simple, because if you think the algorithm is a stochastic algorithm, so you have a random movement of the atoms, and it's really likely that if you move randomly an atom, that this atom will fall exactly on special position. Okay. And another problem that you could have when you solve the non-monadary compounds is if you are describing your systems in terms of a coordination polyhedra, you are introducing into your system more atoms that are really required, and you have that in particular the corner of the polyhedra are duplicate atoms, so they are sharing the same position. Okay, to solve this problem, there is a simple algorithm that used in EXPO, but also in other software, I think in Topaz and our software. And sometimes this method is called dynamical occupancy correction. You have to modify the occupancy factor. The occupancy factor, first of all, is a part of the calculation of the structure factor, and you have to modify the occupancy factor using this formula. Okay, in this formula, you can see you have a sum over, if you have an atom, you have to consider this difference for all the neighboring atoms around each atom. So the consequence of the application of this algorithm, if you have to calculate the symmetry equivalent atoms in the unit cell, and at the same time you have to calculate the distance between pairs of atoms. In general, this algorithm in the software is optimized, but can slow down the computation and the application of a real space map. In other terms, you can see in this plot, if you have two atoms, when these two atoms are at distance larger than a minimum distance that typically is 1 angstrom, the occupancy is 1. When they are getting closer, you have a decrease of the occupancy factor, and only when the two atoms are exactly in the same position, you have 0.5. So you don't have that, you have a modulation of the occupancy factor. You don't have only two values, 1 and 0.5. You have a modulation of the occupancy factor depending on the distance between the two atoms. Okay, and this using this algorithm, you can solve the problem of the spatial positions, and at the same time the problem of the corner sharing between polyhedra. And this algorithm can be sometimes very powerful, because if in a situation where you don't know exactly the chemical composition, you can introduce into your system more atoms that are really required, more but not less. And this algorithm could be able sometimes, okay, to merge the excess of atoms automatically. Okay, good. And in EXPO, the dynamical occupancy correction can be applied using this directive, DOC. And if you write only DOC, the occupancy correction is applied to all atoms into your molecules. Or you can add a list of atoms to which the dynamical occupancy correction will be applied. For example, in this case, I am applying the correction only on the NAC electrons that is expected to lie on special position. Okay, and you can access to the dynamical occupancy correction from the graphical interface. And remember that the dynamical occupancy correction slows down the computation side. So it should be avoided if you don't expect to have a special position. For example, if you are solving organic molecule in a monoclinic space group, you don't expect to have atoms on special position. Okay, the example is that I will show is very simple, is the structure solution of this small organic compound that you can find into the folder PBSO4. Okay, just okay. As we saw before, I will run the program using the parallel version. So mpi run expo and p. Okay, the name of the input file. Okay, then okay. Okay. In this case, we are the starting model contain a tetrahedra corresponding to the sulfate, molecular fragment, and an isolated atoms, and the input file. Okay, this is the input file that I am using as .text. Okay. So I'm using the command %fragment and tetra, the percent fragment fall by the keyword tetra to generate a tetrahedron. And to generate an isolated atoms, I used another keyword called atoms. Okay. And then the command %SNL and the directive to enable the dynamical occupancy correction. So at the end, the program generates the project file and the export. Okay, and just this solution. Remember, you can access to all the 10 solutions from the bottom solution. Okay, and okay, there is another important question. If you are okay. Just okay. This is another example when we are solving this inorganic structure starting for T tetrahedra and 2 octahedra. This is the final result, and an important aspect is that as I said before, we are introducing more atoms that are really required. So we at the end of the structure solution, we obtain a structural model containing more atoms. In particular, you will have that some atoms are merged in the same position, and you have other atoms that are symmetry equivalent to other atoms. In EXPO, there is a tool that you can use to delete these duplicate atoms and rebuild the asymmetric unit that in that case contain only 17 atoms. And we can see the application to this. We have to go from modify, delete duplicate atoms. And you will see, okay, this atom where one oxygen atom was deleted because the asymmetric unit contained in this case only 3 oxygen atoms. Okay. And okay. So we have okay. In some situation, the real source method can fail. In particular, when the quality of your diffraction pattern is not really good. Okay, so the situation could be you are collecting data using your X-ray laboratory data, and you have broad peaks, so you have severe overlap, you have weak scattered, you could have preferred orientation and other problem into your pattern. And this situation, we have non-excellent quality data is combined with large number of degrees of freedom. In this situation, the algorithm can fail to not to locate the global minimum, because the algorithm can find the global minimum, that this global minimum can necessarily correspond to reasonable case structure, just because the quality of your data is not good, okay? So in this case, the solution could be introduce into your program additional chemical information. And in EXPO, you can introduce, or in other software, you can introduce this type of information using restraint. So yeah, for example, anti-bumping restraints, that this is the mathematical contribution to the cost function when you use anti-bumping restraint. You have to use this type of restraint in particular when you see that you have a collision between atoms, you have overlapping between some part of the molecule and other atoms. And in general, anti-bumping restraints are mathematically treated as restraints that are active when the if you have two atoms, when is active between these two atoms, when the current distance between these two atoms is less than a minimum distance. And this minimum distance can be calculated using the van der Waals radii and multiplied for in EXPO for this factor. The default value for this factor is 0.7. So if you in practice increase this distance, you increase the number of pairs of atoms considered in the loop for the calculation of this cost factor. And okay, this is not really important aspect for you, but in general, the calculation of anti-bumping restraint should be combined with the algorithm to filter the pairs of atoms, because it's obvious that you cannot apply if you have a chain of torsion angles, it is not necessary to apply the anti-bumping restraint between a carbon atom in position 1 and carbon atoms in position 3, or carbon atoms in position 1 and 4. You have to consider the interaction 1, 5, and only if these torsion angles are rotatable. Because if you are in a rigid system, it is not necessary to consider the anti-bumping restraint. In EXPO, the anti-bumping restraint can be activated using the directive bump. If you use just bump as a directive, the anti-bumping restraint will be activated only between all pairs of atoms that are oxygen, nitrogen, sulfur, and carbon. Okay. Or you can specify the atoms or group of atoms. Okay. And remember that this time-consuming procedure, and so you have to use the use of this restraint only if you know that you need to use, in particular when the quality of diffraction data is not sufficient. It is not of sufficient quality. Another type of restraint that you can introduce in EXPO is represented by the bond valence restraints. First of all, here you can see the definition of bond valence sum. That is very simple. Okay, just you have this sum. This sum is over the bond valences of two atoms. And so if I have an atom I have to consider around these atoms all the surrounding atoms. Okay. And the bond valence is this quantity, where there are some semi-empirical factor R0 and B that you can find in this file that is maintained by Brown, okay? And you can read out this link, okay? So this is the theory, and this is this is a semi-empirical quantity that you can calculate, and this quantity should be compare with the expected value of the bonds valence sum, that the expected value in general is the oxidation state of the atom. So if you have lanthanum 3 plus, the expected value of the valence bond sum for this atom should be approximately 3. Okay. Or if you have copper 2 plus, should be 2. Okay. Just And this quantity can be first incorporated into the global instability index. So this is a quantity that you can find in the literature, and in particular in the case of inorganic compound, it's used to evaluate the deviation of your crystal structure from the ideal crystal structure, or sometimes it's used for validating inorganic crystal structure, because if you have a unresolved value of this quantity, that means that, for example, you have problem in your structure, you have, for example, space group can be wrong, or you have missing atoms or missing bonds, or can be incorporated as a contribution to the cost function, and so can be used as a restraint in the process of real space method. And in EXPO, there is a graphic tool that you can use to, if you have any organic structure, that you can evaluate the bond valence sum and generate and export an output of this quantity. And you can also apply geometry, say, on bond distance and bond angles, and can be applied using this directive, and you have to specify a target distance and a tolerance of this. If you don't specify this distance, the program tries to assign automatically some value using an internal table of distances. And remember that this procedure can slow the structure solution problem. And interesting application of the use of geometry restraint is when you have a rigid system and you want to make this rigid system flexible. Okay, you remember? I told you that you have to pay attention, in particular when you have a non-planar ring system or condensed ring system, because this is an example. Okay, I'm solving this molecular compound in which I have a 7-membered ring. Okay, I prepare a starting model, use geometry optimization by using DFT in NewChem. Okay, and I build this starting model. Any attempt to solve the structure using this starting model fail. Okay, the reason in this case is simple, if you think, because when you perform a geometry optimization, you are assuming that your molecule is in a gas phase, and sometimes the configuration of a ring system in gas phase is different by the configuration when more molecules are packed into a solid state. So a possible solution to this problem is to break one bond and make flexible this ring. The problem is, if you break this bond, sometimes you can free a lot of degrees of freedom. So the suggestion is to add a restraint to force the closure of ring and to keep the information that there is a connection between these two atoms. And in this case, we are able to solve the structure and to find a reasonable solution. This is the input file that you can use to solve this structure using EXPO. You have to increase the number of runs, you have to increase the number of modes, and this is the input file when you add a restraint. You have to specify the two atoms. Okay, you have to break these bonds. Okay, there is in EXPO also a directive to break a bond called cut. So you can write cut C4, C5, and add a restraint, rest C4, C5. Okay. And there is another approach that you apply. This is a computational expensive approach, because the other approach is you have a conformer generator that is a tool, is an algorithm or software that you can use to generate all possible conformer of your structure, and you have to test each conformer in a structure solution process. Okay, in direct space method. First of all, you need this tool. Okay, there are several free tools, this list, and commercial free tools. Don't use Confab. Confab is an excellent conformer generator, but is not able to modify the the conformation of closed ring. Okay, so you modify only the conformation of the rotatable torsion angle. This is not what you want. Okay, you want the modification of the ring conformation. Okay, and for example, this is the result. Okay, each point. Okay, here you can see the cost function, and each point correspond to each conformance. And you can see that you have for some conformance you have a minimum in the cost function, and this minimum corresponds to a correct structure. As you can see, if you plot the root mean square displacement from the published structure, you can see that these points are correct structure because they are below a value of 0.5 that is considered typically the value. Below this value, the structure can be considered correct. Okay. 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 Another question: the structure solution by real space method can be sometimes, in particular, if you are solving complicated problem and you have a large number of internal degrees of freedom, molecular fragment, we are used dynamical composite correction with restraint. Or sometimes we have to test several cell parameter cell space groups. Can be required a large computational effort. So fortunately today we have the possibility to distribute the computation between several CPU or GPU. Okay, there are several parallelization strategies that today you can use, for example, to in general to parallelize using CPU. The traditional method are MPI and OpenMP, but if you want to use, it's possible to parallelize using GPU, and the most used strategy are CUDA or OpenFCC or Cycle. Okay, in EXPO we have parallelized the program. I have already described very quickly how to run the parallel version of EXPO. You have to use the launcher MPI run. You have to specify the number of tasks. For example, in this example, we are using only 3 tasks. That essentially means we are using 3 CPU cores. And in this case, when you run an MPI job, several copies of the program are created. These copies are called tasks. Each task has its own private memory run independently by the other task, and not necessarily run at the same speed. What is important, if you are performing 10 runs of simulated annealings, these 10 runs are distributed between, in this case, 3 tasks. So the first task will perform 4 runs, and the other task perform only 3 runs. And the program at the certain point, when each task has finished to perform the structural solution, you have an MPI barrier to synchronize all tasks. And at this point, you can use the function of the MPI library to send all the information to the master process, typically the task 0. And when the master process has all the information, it can organize this information. For example, you can sort all the structure model according to a cost function and can perform output operations. So, okay. And to run the parallel version, first of all, you need, computer with multi-core CPU. And, this is not a problem today. Okay. And, you need a Linux environment. MPI should be installed. You have to compile from source code and link the program. This is not necessary if you are using the Debian package, because Debian package contains the EXPO compiled with MPI. Okay, and you can see in this slide some example. For example, the application to this big structure that you have 2 molecules of this compound, and so you can repeat the common percent fragment. The hydrogen were deleted. You have to increase the number of runs, increase the number of moves, and reduce the data range. So you can solve this structure into, reasonable time, 45 hours, okay? using 25 CPU. Okay, that is acceptable considering the dimension of the structure. And okay, if you on Windows you have to use a Linux environment into or VirtualBox machine, or you can use Windows subsystem for Linux. And okay, remember that at the end of the application of real space method, you have to evaluate if your solution is valid. You can use numerical agreement factor. You can use the visual match between the observed and the calculate pattern. And you can, if you run multiple simulated LDNLD, and if you see that at the end of each simulated LDN line, the algorithm converge at the same value, you can increase your confidence about the correctness of the solution. And it could be also important to check visually the crystal packing, if there are close intermolecular contact between atoms, if there are large void space that typically are unlikely, unless you don't suspect the presence of solvent molecule. And okay, could be important to check the network of interactions. And okay, only the last thing is that you have to combine the application of real space method with the validation of the crystal structure. This can be performed in general using the solid state DFT. Okay, and this is a list of some programs. The most important program I use today in crystallography, for example, VAS crystal. I use Quantum Espresso. Okay, and okay, I can stop here. Okay, and
Please.
I would thank you for your kind.